Welcome everybody to this event. We are fortunate to have among us Gabor Domokos. And I must admit, I never get actually if you're an engineer, an architect, a mathematician, but you're a professor at the Budapest University of Technology and Economics, and also head of the Department of Mechanics, Materials and Structures. And you're most famous for either inventing or discovering this strange, beautiful shape that we have here on the left, the Gomboc. Gömböc, okay. My Hungarian is slowly improving. Yeah, so you have to tell this story perhaps yourself, but from what I gather, you had a discussion with Vladimir Arnol'd about the possible existence of a convex shape with only one point of equilibrium, and after many years, you either invented or discovered this shape, and it was immediately recognized as a very intriguing object. It was featured in the New York Times Magazine in 2007 as one of the 70 most interesting ideas of 2007. It was also featured at the World Expo in 2010. So we're very lucky to have you here and talk about how this object sort of touches on a great many subjects. So welcome, Gabor.
Thank you very much. I feel privileged to be here in Oslo at this university, which is the most famous university in Norway and probably also in the broader region. And today's talk will not focus on the history of this discovery. That would be another talk. I am going to talk about some interesting applications which arose after we discovered the Gomboc. But I will go back a little bit in time also. So, who is from natural sciences? Okay, let's zoom physics. Okay, math. Okay, geo. Good. So, since when is NASA operating on Mars? Do you know? Since when are the rovers of NASA operating on Mars? It's 40 years. 40 years. If you see this movie with Matt Damon, you will learn about the details. I won't show it now. I am, among others, I am not an expert on astrophysics, and I am not an expert on Mars exploration, but one of the main objectives of this is a huge project. One of the main objectives is to look for life, but probably not present life, but life in the past of Mars. So, very simply speaking, NASA is operating on the assumption that, say, 3 billion years ago, Mars could have looked like this. We don't know. One of the things which would indicate that it supported life is obviously flowing water. And the recent rover, the Curiosity, landed in 2012. And already very shortly afterwards, it sent back images which were thrilling. Now, those images showed pebbles here, which looked very familiar to geologists because they looked like pebbles which have been abraded in a fluvial environment on Earth. So here you can see John Grotzinger. He was at that point the chief scientist of the mission. He's also one of the authors of the paper which appeared in the Science magazine reporting on these findings that they found these abraded pebbles. So we are talking about a planet 200 million kilometers away and something which happened 3 billion years ago. So small details do matter. And he was the one who called for more mathematical evidence. So to support this claim that these pebbles have been actually transported by water, he was calling for a mathematical theory which would at least partially support that claim. So how do you build up such a model? In general, if you want to build up any mathematical model, the first thing is to look at what's happening in nature. And since we couldn't get a grant to go to Mars, we started on Earth. So in Earth, the other advantage is cheaper, and there are still plenty of rivers around. So you can pick your river. It has to be a good river. It has to be a river. Can you hear me? Yeah? So it has to be a river which is intact. It has not touched by humans. And we found a nice river, as I will show you later, in southwestern Australia. And if you go along the river, you start to understand what's going on. So what's going on is the river is taking the pebbles, lifting them up and dropping them. So that's called saltation. And as they saltate, they collide with each other. And as they collide, they lose small amounts of material, so they change their shape. And we did a very simple experiment. We put a couple of rectangular blocks into a steel drum. And there was, and the drum was kind of lifting them up and dropping them. And so it was qualitatively similar to what's going on in the river. And what we saw was that actually they got rather spherical, rather soon. And that is similar to what you see in the river. So pebbles get rounder and rounder as they go down the river. You can measure this in various ways. So how things approach a sphere can be measured. And one way is you look at a projection of this pebble, and it is like an ellipse, and you measure the elongation of this ellipse, so how elongated the contour is. And if this ratio is going to 1, then you're approaching a circle or a sphere somehow. And the other thing is what is called the isoperimetric ratio, which is the area divided by the squared perimeter. And that is, again, if it goes up, if it is 1, then we have the circle. And if it goes up, then we are approaching the circle. So in this experiment, we saw that we were approaching the sphere somehow. So the mathematical model for something like that would be an equation where you plug in some contour or a three-dimensional thing. And then if you run the equation forward in time, no matter what contour you start with, you end up with a circle or a sphere. So that is the model which we are seeking. But the problem is that there are many such equations. So if you go to the mathematicians and tell them, give me an equation which would produce a sphere, they say this one, and this one. There are many. Which one is the correct one? Now that's a difficult question. And in order to understand which is the correct one, we have to understand some very deep property of this aberration, which is not present in these very qualitative pictures. So this is a dice, but I have here something which is similar. It's not a cube, but a cuboid. How many faces does it have? Anybody has ever thrown a dice? They deny it. They don't admit it, but they did. So 6 faces, okay? So it has 6 stable points. If you have a coin, which you don't have in Norway, I noticed, I came in, people are not using cash anymore. So maybe for you this is a far-fetched analogy, but if you had a coin, it would have 2 stable positions. And there are objects which have more stable positions. So the idea is that there is an integer number which is associated with any object. You can count. You don't have to measure. You don't need a scale. You just count it. And there are other types of numbers. Say, in the case of the cuboid, you can balance it on these vertices, but they are unstable. So it's like balancing a pencil on its tip. How many vertices do we have? I know it's an insult to the mathematicians, but I'm asking the geophysicists. So how many vertices? We got 8 vertices. Good. So we have a count. And because we have a count, we can classify things now. And this is the classification. In the rows, we have the stable points, and in the columns, we have the unstable points. And our cuboid is sitting in row 6 and column 8. And there are other objects here, like the tetrahedron, the octahedron, and the ellipsoid. And the first question is, well, before we ask the first question, there is a theorem which says that if you have an object sitting in any of these categories, then it is always possible to slice a very small piece off and increase either the number of stable or unstable points. So I will show you this. This is the cuboid. We sliced a small piece off here, and I put it down here, and it is stable. There is another one sliced off here. I put it down here, and it is not stable. But you can see that if I slice it down at a good angle, even with a very small slice, I can produce an additional point of balance. Now the inverse question is, how much do I have to chop off in order to reduce this number? So in order to get from 6 stable points to 5 stable points, is it possible to do it just by a very small truncation? Okay? You can do anything, but it has to be very small. Well, in general, the answer is no. You can't do it. But the opposite is always true, and it can be turned into what is called an algorithm. So that is called the Columbus algorithm. And now we go back to the original question. Is this table kind of partly empty and partly filled, or is it all filled? So are there objects in every category, or are there categories which are empty? So we can make a popular vote. Who thinks that there could be somewhere empty categories? Okay, yeah. Well, they are more realistic approach, yes, because we don't know. You see, we don't know. So everybody else thinks that the table is full. I could ask anyone to prove it, right? Because, so what is the evidence? Well, many people thought the table is not full. Many people. People way more qualified than I am. So people are actually seeking the proof that this category was empty. That was looking like a good theorem for some decades. But mathematics has many advantages. One advantage is no matter how smart you are, you can't prove something which is not true. And this happened here. So people were trying persistently to prove this, but they failed. And then somebody came, Arnol'd, Vladimir Arnol'd. He was a very, very famous, great mathematician. And he just suggested the opposite. Instead of trying to prove that it doesn't exist, try to find one. And that sounded like a really strange idea. But finally, we found one. Now, if we combine this result with this algorithm, what is the joint consequence of the algorithm and this object here? That we got it, right? The table is full. Now okay. Then we made the first Gomboc, and we gave it to Arnol'd. It had a number inside. I will go back to the numbers. We gave it to Arnol'd on his 70th birthday, and then he said it was a good job, but now we should do something more serious. And then I was a little bit flustered at the talk. I was nervous giving a talk in front of Arnol'd, and then I didn't understand what he meant, but after that in the elevator, he explained to me a little bit what he meant. So he thought this would have implications for Pebbles. So let's go back to and understand this second hint of Arnol'd. So, okay, here we have a zoo. Now we have a zoo of shapes, okay? It's a full. So where would you put the sphere into this table? Just to make it simpler, I have a sphere here. It was slightly damaged in the baggage handling belt, but it still reminds you of a sphere, okay? Now, you may say it's a problem that it is badly damaged, but it's not such a big problem because, as you can see, a sphere is not a physical object. No matter how precise you make it, it will never be a sphere. Unlike even a Gomboc, which is very sensitive, but it has a finite tolerance. Maybe you can't scratch it more than 100th of a millimeter, but if you scratch it by a millionth of a millimeter, it's still okay. In the case of the sphere, if you scratch it by a millionth of a millimeter, it's not okay. So this is a abstraction. This is a mathematical idea, okay? It's not so I can use a bad sphere or a good sphere. It doesn't matter. There is no physical sphere. Where would this sphere be in this table? Strictly speaking, it's not in the table, but where would you love to put it? So where would you, emotionally, where would you put it just offhand? If I ask you just to put it in, where would you put it? The sphere. It doesn't have to be a rational thinking, just what your heart tells you, where would the sphere belong in this table? Yes? Towards the end. End is probably what you mean is the lower right corner, which is down in the basement. We don't see it. It is at infinity. Who is kind of sympathetic to this idea? It's a very nice idea. Anybody, because we are now people from many departments, anybody having any other suggestion? It doesn't have to be rational, okay? Just emotionally. Where would you put the sphere?
Wouldn't have to be the bottom right corner, but with 0 stable points, and it was like.
So you mentioned 0, okay? So 0 could be in the upper left even, right? Who is sympathetic to that idea? Upper left corner, you see? It's a matter of mentality, and I will show you why. So there is one way to think of the sphere, and there is the other way to think of the sphere. We know that pebbles go towards the sphere. But in this table, how would the pebbles move? Would the pebbles move like this? Or would the pebbles move like this? Are the pebbles red or are the pebbles blue? That is the question. Now, this is rather confusing, and once you start to build up a mathematical theory and you meet some seemingly contradictory things, that means you are in business. That means you start to understand something which is going on in nature. So I got a glass of water from the organizers. If you look at this glass of water, it's very good water, you can drink it. But if I look very closely, what do I see? Really very closely. I zoom in, I see molecules. Well, maybe not with the naked eye, but with a microscope. So the same thing could be viewed as a liquid, but also as an assembly of molecules. So natural things have various scales on which they can be understood. And while these scales are grossly separated here, because the microscopic scale is millions of magnifications down, here they are not as much separated, but they are still separated. So there are two scales, and both the blue and the red is happening. But if you look very closely, then you see the blue, and if you look with, well, we don't know yet. So what would be your intuition? What would we see in nature? Since probably most of you haven't looked at pebbles, I have to ask the question, who is using a liquid soap at home? Okay, now the opposite, a bar soap. Good guy. Because if people who use the bar soap, they have better intuition about this. Because this is the model of a bar soap. So if you want to understand this, the cheap experiment is to buy a piece of bar soap and then clean yourself regularly. And watch what's happening to the bar soap. This is the bar soap initially. Now, after 2 days, assuming this regular procedure, this will look like this. And if I put it down, it will still have 6 stable positions. Now, after another 2 days, the bar soap will look like this. And if I put down, It will have two stable positions here. But here, I cannot balance it anymore. So it lost two of them. And if you are really a very clean person, then within 1 week, you will have something which just has two stable positions. Now, the cheap way is to buy the bar soap. We did it the expensive way. We ran the partial differential equation forward, and we printed out in 3 dimensions the solution set. That is just for the mathematical audience. That's very expensive. Now, so what we see in nature, the global scale is the red scale, and which I will not explain now. This seems to be the deep scale somehow, the interesting scale. This is what the partial differential equations are average things. That is what they tell us about the red one. So, okay, so now we know that we need an equation. Now we go back to the mathematicians. Okay, we tell them, okay, we need an equation which goes to the sphere, but it does in a very particular manner, so it gets rid of the balance points. Now they scratch their head. If we had done this 40 years ago, they would have scratched their head infinitely because they didn't know anything. Now, there are a couple of people who already know that there is such an equation. And it's a famous equation, but not for Pebbles, I am sorry to say. This is the Poincaré conjecture, which was solved in 2002, and it was very few mathematical results make the headlines in the New York Times. This was one of those. And the Poincaré conjecture, I can't tell you about. First of all, I don't understand it in detail, but it was about shrinking things onto the sphere in various dimensions. And in 2 dimensions, 3 dimensions, and high dimensions, they knew it. In 4 dimensions, they didn't know it. But in order to prove this was a topological conjecture, but in order to prove it, they created equations which did this job for them. And by accident, these equations happen to be almost the same equations which abrade Pebbles. It's very curious. So I just mentioned Richard Hamilton, who invented this whole machinery, these equations basically. And then Gregory Perelman, who actually did the proof. But as they worked on the proof, this was not just one thing. They were working on this for decades, trying to understand these equations, at first in 2 dimensions, then in 3 dimensions. There was one small result in 1987 by Matt Grayson saying that if you take the 2-dimensional case, it is approaching the circle in such a manner that it gets rid of balance points. So that seems to be the case. That is what we are looking for, an equation which goes to the sphere and gets rid of the balance points. This is the good news. The bad news is that in 3 dimensions, this is not true. In 3 dimensions, balance points may increase or may decrease in this type of equation. The last bit of news, which is again good news, is that the probability is unequal. So it is an asymmetrical thing. And there are barriers which would prohibit Pebbles to go beyond those barriers. One of the reasons is friction, which is not present in these equations. And now, this seems to be a meager information if we look at 1 pebble. But if we look at 1 billion pebble, and we play this game for 1 million years, that we throw the dice, which is a asymmetric dice, so the probability of going up is always larger than the probability of going down, what will be the end result? We take 1 million pebbles somewhere here, and we play the game with them for 1 million years. Well, they would be crowded somewhere up there. And probability theory gives us a very, very exact picture. This will be an exponential distribution. So now we have a theory, which has an equation which goes to the sphere in the manner which we like, and it gives us a very definite prediction what would be the invariant density function for pebbles. So now we go back to the beach and test the pebbles. Actually, we did this before we knew the Gomboc. We went to the beach. I was desperate. That was 10 years after Arnol'd told me that there could be such a shape. And I had no idea still. I mean, I knew that I knew many things about the shape, but I didn't know whether it existed or not. And I convinced my wife that it would be a good idea. So we had 1 week vacation in Greece. That was a yearly vacation. And I told her that the best way to spend the evenings would be to classify pebbles based on the Poincaré-Hopf theorem, so counting these numbers. And in order to make this really serious, we need 2,000 pebbles. So this is a bifurcation point for a marriage. It can go 2 ways. And just to understand, in our case, my wife, after 1,200, I was exhausted. I mean, I wanted to give up. My wife insisted that we do the 2,000 because I suggested the 2,000. So I had to suffer through this 2,000 pebbles. And we didn't find the Gomboc shape. So I got really depressed after that, because I was thinking about this for 10 years. And I saw that if, you see, there are so many pebbles, so I saw that if this thing exists, it should be among the pebbles. So if you look at enough pebbles, you should find it. You can understand this was not a conventional approach to a mathematical problem, but it was a legitimate approach. But we didn't find it, so I got very depressed. And for a while, I didn't do any research on that. But 10 years later, after, okay, we found the Gomboc, then we gave it to Arnol'd, and then he said, look at the pebbles, and so on and so on. And I showed him this slide when I gave him the Gomboc, and he said, that was your best slide. And I thought because of the story with my wife and everything, and ha, 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 I said, this is a funny slide. He says, no, he was not enjoying that part. He said that, look at that. This is what you see. This is what? This is what? This is the geometric distribution, what you see. So if you go back to this and you superpose what we measured on roads, it's the same thing. And he saw it. He probably also saw the partial differential equation in the background. She said, you look at that equation, because there is something there. This is something. And I had to admit that it was there. I haven't seen it. Okay? So this is good. This gives us the good stationary distribution. But it gives us more. It not only tells us where the pebbles will get, it also tells us how they get there. Because if you study this process, this random process, it tells you there is a fast transition at the beginning. So the numbers will go down, and then they will kind of go around. So we went, as I said, to southwestern Australia, to the Williams River. This is the Williams River. And we measured the pebbles at 12 locations along the river. And if we plotted those measurements, you could see exactly the same thing. So this is the computer simulation, and this is the raw data. So you can see that it doesn't only tell you what is the end result, it tells you the process. So this is the good equation. And if you go to the lab, there's no way you can get it wrong. It is so robust, this phenomenon is so robust, no, you cannot mess it up. You always get this kind of result. So now we have an equation. We are firmly convinced that this is the good equation. There is no doubt. This equation was based on understanding how many equilibrium points the body has. But now we can forget it. Now we have an equation. And this equation will tell us exactly what is happening. This is very particular. So for example, this is the isoperimetric ratio. And this equation, okay, in this experiment, as you see, we start with a rectangle and end up with a circle. So the isoperimetric ratio should go which way? Who understands what is the isoperimetric ratio? And I may want to add a comment on that. So the isoperimetric ratio is a number between 0 and 1. And for any planar, or you can talk about spatial object, it is between 0 and 1. It is only 1 if that object is a circle or the sphere, and it is 0 if that object is like a needle or very elongated, very flat. So it is a number which measures how close we are to the circle. Okay, it's just a scale between 0 and 1. It is between 0 and 1. So if you look at this, what should the isoperimetric ratio do? So we start with a rectangle and we end up with a circle. It should go up. Yes. And it did go up. But now this theory, this equation, if you run this equation, it tells you exactly how it goes up. Not just that it goes up, it tells you exactly how it goes up. So it tells you that it has a vertical tangent here, it has a horizontal tangent here, it is a convex curve. So it tells you everything about this curve. And then you superpose your data, and the geologist would say that, because, okay, the mathematician would say, oh, this is very bad. No, it's very good. In geology, this is very good. So this tells you that this is the right equation. Now we are not only convinced, we are firmly convinced that this is the good equation. And now we go to Mars, because we are so firmly convinced that now we can go to Mars. This is Mars. So this is the Gale crater where the Curiosity has landed. This is the landing ellipse where they wanted to put it down. And actually they put it down here because they thought they might find some remains from ancient rivers. So that was the actual idea, part of the idea. And that was the suspicion that there could be an alluvial fan here. So there was probably a river, and this was the alluvial fan. And what you can see here is the route of the rover, this yellow line. So this is a detailed view. And then at that point, we got in contact with NASA, with Grötzinger. And all the data which NASA collects is public, but the real thing is to know which data is the interesting data. So he knows his ways around on Mars. So if he would be dropped like Matt Damon, he would blindfold it. He would get around. He knows exactly what's going on Mars. So he told us exactly which are the good pictures. And then he said, okay, give me an estimate on how far these pebbles may have traveled on Mars, because we have a good guess based on the morphology. And if your computation gives something which is in the same ballpark, then we could think of this as a good way to understand things. So we spent 6 months calculating, because, okay, we took these pictures. We took the contours, other contours, and now we have this curve, and we put this data on this curve. Seems to be very simple. It is very simple, but you have to do it very carefully. So now we know that we believe that this is a universal curve. And we actually checked that what I didn't talk about, that the initial condition, I mean the fragments on Mars are the same as the fragments on Earth. So now, because we made these measurements, we know that the loss of mass of these pebbles is approximately between 10 and 20%. So simply speaking, just by looking at the contour, we can tell, well, what was the original size of the fragment. Now that doesn't seem to be a complicated thing, but it's good news to geologists. Geologists didn't have this tool. So we did it once, twice, 3 times, 4 times, 5 times, many times, and each time we got the same result. We did it in different ways. Each time we got 30 miles, or 50 kilometers. So we sent an email to Grötzinger saying 50 kilometers. And he said, it's okay, we are in business. Because they had the same idea that this distance here is about 50 kilometers. So these rivers probably brought down these pebbles from these mountain ranges. And so you see this is 6 kilometers. So the total length of the river is, we are not saying 51 kilometers, we are saying 40 to 60, okay? But this was a very good guess. And you can see that he is smiling on this picture. So actually, because these computations were so much different from what they did, they were just looking at this and had this guesswork. And we were looking at the pebbles, and we gave this exactly the same number. That is now counted as very small, but additional evidence that there was fluvial activity and not small, major fluvial activity. So we are talking about a large number of larger rivers because there was other data which we compared them. So this is Sir Michael Berry, theoretical physicist, and he listened to an extended version of this talk. And he summarized it, that saying that the Gomboc is not part of nature. Part of nature, it exists nature, but only as a dream. So every pebble wants to move towards the Gomboc, but it never gets there. So if you want to get a Gomboc, going to the beach and to wait is not the most efficient algorithm. You could get lucky. I mean, you could get lucky. And maybe at the end, I should also mention that there are these special pieces, which maybe you mentioned in the introduction. So there are some pieces which are carrying numbers, which are, the problem is with this that they are very sensitive. Okay, I got a Gomboc here. It's a very visible one, environment-friendly, green Gomboc. This is something very new. So originally, we could manufacture these things only with computer-controlled machining. They are so sensitive. I can tell you, this is not computer-controlled machining anymore. I can tell you why. But these guys, which have the numbers inscribed, then that changes a little bit of the mass. So in order to, the geometry may be changed. So in order to make one of them, for each one, you need a special tool, which is discarded afterwards. So these places put them on exhibit, and we are very proud of this. Thank you very much for the attention.
Thank you very much for making us travel wide to Australia and further away even. Yeah, by the way, geology has been kind to offer us pebbles, edible pebbles with one static equilibrium point.
Soft pebbles.
Soft yes. Pebbles. So please have one. And yeah, let's take questions here.
Any kind of question is welcome.
So by the way, I'm Snorre from the math department, and Caroline from the library will pass around the mic.
Yeah.
Thank you very much for your nice lecture.
Thank you.
I have one question.
Yes.
Pebble or Gomboc, the two words you are using all the time. I am not a mathematician.
Okay.
How will you describe what is a pebble?
What is a pebble?
Yeah, what is a pebble? Not mathematically.
Well, it's not a mathematical concept. Well, a pebble is mostly used in geology. It's in sedimentology, there are different kinds of particles, and pebbles are the sedimentary particles which are in the medium size range. So they're not very small. The very small ones we call sand. The medium ones we call pebble, and the larger ones we call boulders. And the very large ones we call asteroids. They are out there. I am not joking. I have actually slides about, we were thinking about asteroids as well, because these equations are geometric equations, and the nice thing about geometry is once you got the equation, it applies on all scales. So it applies to sand, it applies to pebbles. So this size, it's between, I would say, 1 centimeter and 20 centimeters, or maybe a couple of millimeters and 20 centimeters. That is a usual range for pebbles. I am not an expert, but so the medium range for these particles which are being carried, where you can see pebbles in large numbers are on the beach. So there are two types of beaches, the sandy beaches where you have sand, and the other ones where you have pebbles. On a medium pebble beach, the number of pebbles on a medium pebble beach is comparable to the number of stars in the galaxy. And we are just talking about pebbles, not about sand. So that is the reason why this kind of study might be interesting, because it tells us about, there's a huge amount of information buried in the shape of the pebbles. And what I was talking about is maybe not the best way, but one way, try to decode this shape, try to get out information in a mathematically justified manner out of the shapes which are out there. So this is what is meant by Pebble.
Okay, thank you very much for your
You're most welcome.
reply. Also, another thing, how will you define a Gomboc?
How do I define it?
You are talking about
Yes, that is a Gomboc. Yes, this is a shape which has only this one stable and one unstable balance point. This shape was not known to exist for many years. And that is something, it is not unique. There are many other versions, but this became famous because this is the easiest to manufacture, and that is best known in the media. This version is best known in the media. That is called the Gomboc. And the reason it's called the Gomboc is purely hidden in the Hungarian language. We know that any such shape would be very close to the sphere. So we have this table of shapes. In any category, we can have shapes which are very far from the sphere, except this category where every object has to be close to the sphere. It's kind of spherical. And in Hungarian, the sphere is the gömb. So the Gomboc means that it's kind of a spherical thing. And that gives you also the difficulty, why it was so difficult, why people couldn't understand whether it existed or not, because in this region or intuition completely fails, at least mine. I am not talking about other people, but when you go close to the sphere, anything can happen. That was why I was explaining that if you go to the mathematician and tell them, I need an equation that goes to the sphere, there are so many equations because there are so many ways to approach the sphere. The sphere is a highly degenerate thing. You can go to the sphere. And that is why Arnold's second hint that you should take this property, this number, in account and see how the number changes as you approach the sphere. That is a crucial thing because this singles out the good equation. So this is called the Gomboc. And that is also here. And these are individual pieces which are at some famous institutions on display.
Thank you very much.
You are most welcome. Any other question? Yeah. Shoot. Oh.
Very nice presentation.
Thank you.
In this list or table of shapes you showed, you had this red line between 1 and 2.
Yeah.
So, as far as I understood, it's like a barrier that
Yes,
in nature cannot be crossed.
Yes, that would be worth another talk. So, but I can tell you some things about that. So there are many reasons. So shape would move toward the Gomboc, but there are 3 reasons why they would stop here. And I can't tell you the kind of reasons. One is friction. Friction is not included in these equations. It is an extra thing. And if you take a flat object and let it slide, then it would become more flat. And if you take an elongated object and let it roll, it would get more elongated. So therefore, friction tends to make things more flat and more elongated. And that would prohibit anything to go beyond those red barriers. That's a physical reason. There is a much nicer reason, which is more difficult to explain, a deeper reason, which is a purely mathematical reason. It has nothing to do with friction. It's independent of this, but it is also actually, I can just indicate the kind of reason what I'm talking about. So in this case, we are counting the critical points where the reference point is at the center of mass. But we could count critical points where the reference point is offset a little bit. It could be equally natural. So I'm always referring to uniform density. Why? So one could think not of this particular case where the center of mass is just sitting at the right place, but at a collection of possibilities, how they change as things erode. And if you think about that, then it gives you so in each object, you can move around this reference point, and in some location, it would give you more critical points. In some location, it would give you less critical points. And what actually the equation is acting on is not the number of critical points of the homogeneous object, but the equation is acting on the maximum of these things. Now, the minimum of the maximum is not the Gomboc, it is the ellipsoid. And that is a much nicer thing. That would need more detail, but that's a purely geometric, beautiful thing, and that tells you why things stop there. They could go beyond that because there is this fluctuation. They could go beyond that occasionally. Now, there is a third reason. The third reason is that I told you that there are unequal probabilities, but they are not uniform. So as you move, the ratios change. And as you approach this barrier, the odds that you can go... That was an asteroid. That you can go beyond that. So in order, what is the amount of material you have to chop off? I started my lecture with this one. How much do you have to chop off in order to get rid of one balance point? This is called the robustness of a solid. Now the robustness is increasing as you go towards the Gomboc. And here you can believe me that, say, 30%, you chop off 30%, you can get rid of one. But if you have a tetrahedron, it's getting more tricky, and if you have an ellipsoid, it's even more tricky. So this robustness, this is a geometric concept, so there are many reasons. So we just see, I don't know what would be the best. For me, the most beautiful is what I just mentioned, the mathematical reason, but the physical reason is equally legitimate. Yeah. You had a question.
Yes, I was wondering what would change if these stones were not carried by the river, but by a glacier that then just suddenly melt?
Maybe everything. So abrasion has different modes. Today I was talking about one mode of abrasion, and that was deliberate. That was fluvial abrasion. Because on Mars, the suspicion was that this was produced by a river. There are other modes of abrasion, and geometrically they are very easily understood. We are just discussing this problem with Snorre, that in a fluvial environment, pebbles collide with like-sized objects, so the same kind of pebble or with the riverbed. So I am being abraded by things which are my size or larger than myself. A completely different environment is in the desert, when the pebbles or rocks are being abraded by sand. And that gives you a completely different evolution equation. Not these flows, the curvature flows, which I was talking about, but the iconal equation. The miracle is that and it gives you completely different shapes. It doesn't go to the sphere. It gives you very funny shapes. The miracle is that even under the iconal equation, which is a different torque, the number of balance points is going down. That's rather strange. So there are different abrasion modes. Maybe in a glacier, if it is being rolled or moved and among smaller particles, then maybe the iconal is the dominant. I don't know anything about glacial abrasion. Or maybe it's friction. That is a third mode. So there is this sand blasting mode where small things collide. There is the fluvial mode where large things collide, and there is the friction mode where things don't collide anymore. They are just being slidden or rolled. So any of those modes would result in a completely different geometric evolution. So the shapes which you see would be not spherical, but which would constitute the topic of several talks. It's interesting to show that in each case, this number is going down. That was probably a visionary thing from Arnol'd. This seems to be a common theme. So if we want to be philosophical, I don't know whether there are anybody from the philosophy department, So biological evolution tends to make things more complex. If you look at ourselves, we are very complex. The dead nature seems to make things more simple, just no matter what it does. Other question?
Sorry.
Yeah,
So you said there are more of these Gomboc shapes,
infinitely many.
but is this true also for the remaining shapes in the period? Or in the table?
Yes, yes. In each category, there are infinitely many
But
shapes.
then there is also some transformation that gives you the one shape from all the others?
We don't know about such a transformation. We know very little about this table. So mathematically, that is just a comment for the mathematicians. We don't even know whether where the Gombocs live, the set is a connected set or not connected set. We know very little about this. We know that there is some distance beyond which they don't exist. So they have to be close to the sphere. The reason why this shape became famous is that this can be manufactured. The first shape which we proved that it existed was 10 to the minus 5 close to the sphere, and it could not be manufactured. This is the largest versus the smallest radius in this object is 1.15, which is pretty far from the sphere. And we don't think that you can go much further, maybe 1 in the second digit. So that is the reason why this can be manufactured. And we don't know much about them. So Michael Berry, whom I said, he's now looking at so what is the minimal number of spherical harmonics to produce a Gomboc shape? It's not known. And very little. I think 99% of the questions are unknown. It's a fair statement.
Thank you.
Yeah.
I'm just wondering about, you said you computed about 50 kilometers because what you observed on the Earth and on the Mars. And the model doesn't factor in gravitational modes, so, or does it?
Oh, gravitation does matter.
The gravity is different.
Oh, absolutely. Gravitation does matter. So just to put it simply, we told the geophysicist how much mass these pebbles have lost, and he computed how much they have traveled, but he took into consideration everything, in particular the gravity on Mars, and the type of rock, because he knew exactly what type of rock we are talking about. So there is lots of data on Mars which had to be incorporated in this, and I didn't mention it. So thank you for that question. Yes.
Okay, thank you very much, Gabor, for telling us about how nature dreams. The Science Library has a gift for you.
Thank you very much.
The shape of a soap bar.
Thank you. Now I can practice at home. Thank you. I will open it in Budapest. So if anybody wants to play with it, it's here.